Welcome to Lecture 1.3, Direct Products and Sums. In the previous lectures, we learned about vector spaces and subspaces. We learned about what it meant for a subset to span, to be linearly independent, and to be a basis. In this lecture, we will see how to create new vector spaces from old ones. We will see several ways to multiply vector spaces together. And we will learn how to construct the complement of a subspace, the direct sum of two spaces, which will involve the complement, and the direct product of two separate, unrelated vector spaces. To begin, we need two very basic results. The first one says that every subspace Y of a finite dimensional vector space is finite dimensional. And the second part says that every subspace Y has a complement in X, which is another subspace Z with a property that every vector in X can be written uniquely as the sum of something in Y plus something in Z. And then that the dimension of X is going to be the sum of the dimension of Y and the dimension of the complement. That will come for free. So let's prove this. So first of all, part A, every subspace is finite dimensional. So let's just start by taking a vector. So let's pick, say, let's call it y1 in y, and then we can extend this to a basis. And then extend, so this is obviously linearly independent. Well, I should say if we pick a non-zero y1, but why would you pick a zero vector? So extend this to a basis, y1 dot 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 yk of y. And now by a previous lemma that we proved, that means that k, since this is a linearly independent set, it has to be less than or equal to the dimension of the entire space x. So by, I think I called it lemma 1.1, k is less than or equal to the dimension of x, which we know is finite. So that does part A. For part B, well, we have a basis for y, so we need to extend that to a basis for the entire space. And that's something that we have proven that we can do. So for part B, I should say this is A and then this is B. We can extend this basis to the basis for y to a basis y1 up to yk. Let's call it zk plus 1 all the way up to zn of x. And then let's let z be the span of zk plus 1 all the way up to zn. So notice by construction, this thing has dimension k, and y has dimension k, and z has dimension however many of these there are. So that is n minus k, and the dimension of x is n. So again, the second part comes for free. This works. I don't think I need to prove that these are complements. In other words, that because this is a basis, every element can be represented uniquely as a linear combination of these guys. So let's just say that this works and put an end of proof box here. Okay, so let me make a couple comments. First of all, this is in no way unique. I mean, all we did is we took a space. So here's how you should think of this. Like y is a vector space like this, like a plane, and we just extended it. So we had a basis for y, and then we extended it to a basis for x by just adding in any other vector that we wanted to. So in this case, if we did this, here is that vector z. So I know often when we are thinking about complements, we're thinking about orthogonal complements, because that might be something we've done before, but we haven't defined the notion of orthogonal or angle. So really, any any line like this that does not lie on this plane, assuming this is an R3, is going to be a complement. You can still write every vector in this space. So this vector over here, we can still write as we can decompose it as something in Z and then something in Y. This leads to the definition of the direct sum. We say that a vector space X is the direct sum of two subspaces Y and Z if they are complements of each other. More generally, it is the direct sum of M subspaces if every vector in X can be expressed uniquely as a sum of corresponding entries in each of these subspaces. So y1 up to ym, where yi is in big yi. And we write this as follows. So we use this plus notation with a circle around it. Now I should mention that by definition, by construction, you can't just take two arbitrary vector spaces and put them together as a direct sum. The direct sum only occurs when y and z are subspaces in the same big vector space. In contrast, the direct product is a construction of how we can take two somewhat unrelated vector spaces. Now they have to be over the same field, but one could be a space of polynomials, one could be a space of n-tuples, and we can put them together. So by definition, this is the set of ordered pairs, x1 and x2, where x1 is in the first space and x2 is in the second space, and addition and multiplication are defined component-wise. We denote the direct product with this x the same way that we would denote the Cartesian product of the underlying sets. And really, this is a vector space where the underlying set is the Cartesian product. So compare this to the direct sum, where we use this plus with a circle around notation. Okay, so quick proposition. I'm not going to prove this. I'll say a bit about how you would prove this. It's fairly straightforward. That the dimension of the direct sum and the direct product is additive. So the dimension of the direct sum of M subspaces is the sum of the dimensions. And similarly, the dimension of the direct product of M vector spaces is the sum of the direct products. Now remember what the dimension is. It's just the size of a basis. So to prove these things, you need to come up with a basis for the left-hand side, or the vector space here, which is equal to, whose cardinality is equal to the right-hand side. And I'll leave this as an exercise, but let me show you how it works just by looking at two subspaces. So suppose we have the dimension of y, or the direct sum of y and z, like we had in the previous slide. And let's suppose that b, y is a basis for y, so that's y, say y1 up to y n, and suppose a basis for z is z1 up to zm. Then I claim that just the union of these, so by union bz, is a basis for x. So the dimension is additive. It's just the it's because cardinality of these disjoint subsets is additive. And I'll let you figure out how to extend that for m of these. It's straightforward. I think notation is the hardest part. Now for direct product, you have to be a little bit careful and claim that if you were to take, even though y and z are subsets, or subspaces of the same space, you can still take their direct product. That still works. And here I claim that a basis of the direct product is going to be the following. So y1 comma 0 all the way up to yn comma 0, and then 0 comma z1 up to 0 comma zm. So in other words, every ordered pair can be written uniquely as a linear combination of these guys. And obviously, the cardinality of this is just the dimension of y plus the dimension of z. And once again, I'll let you extend this to m tuples, or m factors instead of 2. I think again, notation is probably the hardest thing. I think the concept should be clear. So it's all about figuring out what a basis is and counting that. Now, one thing that you might notice here is that though these vector spaces, the direct sum, the direct product, are very different, they should be isomorphic in some senses, because we're really just dealing with the same things in both of these. One of them is a linear combination of these n plus m vectors, and in this case, it's the same thing. They're just organized a little bit differently into ordered pairs. And this is true more generally. For example, let's let x be R4, so the set of all 4 tuples of real numbers. Let y1 and y2 be the following 2 subspaces. So y1 is a subspace, it's 2-dimensional, where the last 2 entries are 0, and y2, the first 2 entries are 0. And let's let x1 and x2 both be R2. So these are 2-dimensional spaces. These are isomorphic to y1 and y2, but they're still very different. Now, this is a set of 4 tuples, and these are a set of ordered pairs. Clearly, x, as R4, is the direct sum of y1 and y2, since every 4 tuple, ABCD, can be represented uniquely as AB00 plus 00CD. Also, the direct product of x1 and x2 is technically, it's an ordered pair of ordered pairs. So it's A comma B comma C comma D. Now, it should be clear that x, in other words, the set of all of these guys, is naturally isomorphic to the set of all of these guys. I mean, really, is, the difference is just cosmetic. You got a couple of extra parentheses and a comma in there. So we have a canonical bijection between this set and this set, which is linear and is an isomorphism. And this is not a proof, but it at least suggests why, if you take 2 subspaces, you take their direct sum and their direct product, what you get are isomorphic vector spaces. They're different, but they are isomorphic. It's important to notice that things go wrong if the dimension is infinite. So for finite dimensional spaces, there is no difference up to isomorphism of direct sums versus direct products. However, this is not the case when x is infinite dimensional. So consider the following vector space x, we'll call it R infinity, which is just the countable direct product of copies of R. So that's just a set of all sequences, A1, A2, A3, etc., where AI is a real number. And then for each integer I, we can define a subspace xi to be 0 everywhere and non-zero in the ith coordinate. So x1 is this sequence, A1, 0, 0, 0, 0. x2 is 0, A2, 0, 0, 0, and so on. Elements in the direct sum of these subspaces are, by definition, finite sums. So we are only allowed to add up finitely many things. So I will write x to be xi1 plus xi2 plus all the way up to xik, where xij is in some big Xij. Now, this double subscript notation I'm using because it lets it be open as to what these indices are. So I'm not requiring, so let's put it this way. If I were to write x1 plus x2 plus xk, where xi is in big Xi, then I'm really restricting myself to the first k of these things, and I don't want to do this. This might be the second one, this might be the 2 millionth one, and this might be the 3 billionth one. So it's just a little bit of notation that I think we'll be using a lot throughout this class, so I want you to get used to. So because of this, we can write the direct sum as the set of sequences that eventually are all 0. So everything beyond this index ik is going to be 0. Now, maybe there's a lot of zeros in these first k entries as well. We're not saying these are all non-zero, but we're saying at some point they're all going to be zeros. So notice that the set of these is strictly contained in the set of all sequences. So for example, the sequence 1, 1, 1, 1 indefinitely, which is in the direct product, is not in the direct sum. So elements in the direct product you should think of as sequences, whereas elements in the direct sum are finite sums. So for example, you can think of an element as like 3e1 minus 5.25e4 plus 78e11. And so here, I mean, e1 is the vector 1, 0, 0. So it's just like what we would do in finite dimensional spaces, but it goes on forever. So e2 is 0, 1, 0, etc. So the reason for this is both of these things are vector spaces, but this, you just got to be careful when things are finite dimensional. So this 1, 1, 1, 1, if we try to compute the norm of this as we normally do, like the Pythagorean theorem, technically this is called the L2 norm, but that's a topic for real analysis class I won't get into. Then the norm of x is, in quotes, which means I'm lying, it's 1 squared plus 1 squared plus 1 squared plus etc. equals infinity. So that's not saying that this is not a norm vector. This is not a norm vector space. You have to be careful as to how you define the norm. This norm doesn't work because what you don't want for a norm or a magnitude is vectors to have infinite length. So there are ways to put norms on this vector space. So for example, you could define the norm of a sequence to be the maximum of all of the entries. And so now this sequence is going to have length 1 instead of length infinity. So a good rule of thumb here is when things get to be infinite dimensional, all hell could break loose. Like things start breaking because you have multiple ways of defining things like a norm or convergence. I like to think that in the finite dimensional case, in linear algebra, everything you ever want to be true is true. Not so much in the infinite dimensional case. In the field of real analysis, everything you want to be false is false. There's incredibly weird counterexamples about functions that are continuous but nowhere differentiable and all sorts of things. And once you take linear algebra and you get into infinite dimensional space, you got to talk about convergence. And that now turns into an analysis problem. And that's where everything gets turned upside down and everything you want to be true, well, not everything, but a whole lot of things you want to be true are false. So mostly in this class, we will stick to finite dimensional vector spaces, but I think it's still very helpful to understand the difference, especially this example, which I think illustrates really well what the difference between a direct product, an infinite direct product, and an infinite direct sum is, and how and why they are different. So keep this example in the back of your mind, and also realize how if these were to be finite, how then you don't have this problem with this norm, and these two spaces are going to be isomorphic. Okay, so actually that's the end of the lecture. I thought we had another few slides. So in summary, in this lecture we talked about how to multiply two subspaces together to get a new vector space. In the next lecture, we'll do the opposite. We'll take a vector space and take a subspace, and we will divide out by that subspace. So that's called taking a quotient, and it will involve taking or constructing a new vector space involving equivalence classes of that subspace. So stay with us.